All right. Good morning and welcome all. Hope you had a nice vacation. I did nothing much and it was very good. We have only a few classes left. And today I want to pick up where Anna Kreshuk left off in our Christmas special. She told you essentially about Multicut and its applications in biology. Multicut is also known as correlation clustering and is an important method for the partitioning of signed graphs. And I want to recall how that can be used in computer vision. I want to give another example of where that can be used. And then especially want to dive into the math with you. So here's my version of Anna's talk. We have I'm wondering what's being recorded right now because I don't see on my screen what you see on yours. Hold on. So here's my version of Anna's talk. This is one application where multicut or correlation clustering is relevant. Now you see a brain imaged at various scales from the macroscopic via diffusion tensor imaging. So this is something you can acquire non-invasively with a magnetic resonance instrument. This is a famous image from the visual cortex of monkeys, so that's starting to be invasive here. This is in the late 19th century, thanks to a breakthrough both in staining and also in microscopy, that we could start looking at individual neurons. So this is a beautiful drawing by Cajal. And then today we have serial sectioning electron microscopy. And this is here drawn roughly at the same scale. So this electron microscopic image is very broadly at the scale of this drawing of Cajal. And I want to show you some of the raw data, which was acquired by Davi Bock in his PhD thesis. So he's one of the people who really made a difference with their PhD work. He built an electron microscope, which was 2 or 3 stories high, and could image, sizes of tissue that were not accessible before. So here we have mouse visual cortex, and I'm now going to zoom in. So what you see, the bright spots, these are the cell bodies, and then I'm zooming in and in and in. And here you start discerning these individual neural processes. Yeah? So each of these small things here are branches of dendritic arbors. And we can zoom in a little more. And when we zoom in more, you start to see synapses. So these are the vesicles with neurotransmitter here, some postsynaptic density, that's the synaptic cleft. And then to understand how the brain is wired up, we would like to track each and every one, or trace each and every one of these processes across depth. Yeah, so these images now are across depth, and you can see that some are easier, some are harder to trace, but this is the challenge. So this is the kind of resolution that you have, across this entire slice of brain, and currently people are working hard on trying to really trace the wiring diagram of a full fly brain. And just for a fruit fly, the tiny thing that sits on your banana, it has an even tinier head with an even tinier brain in it. That's already hundreds of terabytes of data looking very broadly like this. So it's a challenge both in terms of sheer size of data, but also in terms of difficulty of the task. Well, this mouse visual cortex at this scale here, I've, very approximately, this entire wall of our lecture hall would be the size of the brain of a mouse, which is not a big thing in itself. Yeah? So that's the data, and over time, something like a canonical pipeline has evolved. Anna has been showing you that we can go from the raw data to a pretty good boundary map using neural networks. Then what people do typically is that based on these boundary detections, so-called superpixels are found. These are groups of pixels which are clustered together, where we very strongly believe that these are a true oversegmentation. So the idea of a superpixel is to reduce the number of objects that we're dealing with from billions and billions to just millions and millions, to make it more tractable. And each superpixel should fully reside within one cell. So it's okay to break up one cell into many superpixels. It's okay to make this big one here into many small superpixels. But we strongly want superpixels that do not cross a true boundary. All right, these superpixels are the abstraction that we're going to work with. So we consider each superpixel as a node in a graph, and then we try and estimate between each superpixel and its adjacent superpixel. So we consider this as two nodes in a graph with an edge in between, and then we try and estimate if or not across this edge, if we believe that they should actually be merged, so we make this an attractive interaction, or if they should be kept separate, a repulsive interaction. And so then we have an undirected edge-weighted graph with edge weights that are larger or smaller than 0, or attractive and repulsive edge weights. And then we need to partition this into the final result, which can look something like that. And then we hand this back to biologists who hopefully make sense of it. Good, so this is one application of multicut or correlation clustering. I'll give you another example. So use cases are, on the one hand, image partitioning, or instance segmentation, or you can use at least approximations to this to detect communities in social networks. Community detection. All right. So in terms of okay, these are the pictures that you've seen. In terms of an abstraction, what we consider is that we are given an undirected edge-weighted graph. The task is to find a, I'm going to use a non-technical term here, find a harmonious partitioning. What do I mean by that? So in such a graph, we have a couple of nodes, or sometimes these are called vertices, and then we can have interactions. I'm going to try and use colors that are friendly for red-green blind people. So let's say perhaps these are attractive interactions here. And let's make this one here repulsive. And if here each node was a person, and if this is how people like or dislike each other, then there's a very obvious solution to please everybody, namely to put a cut here, and we would get out two groups or two clusters, and everybody's happy. Everybody's happy means whoever wants to be together is together, whoever does not want to be together is not together, and all is good. Alas, in real life, things may be more complicated. So perhaps there is an additional attractive edge here. And now we need to argue, or we can start arguing, okay, if this attractive edge here is stronger than the repulsive edge, okay, we cannot please everybody, but attraction being stronger than repulsion, maybe let's remove this cut. And let's put everybody in one group. And this is essentially the correlation clustering problem, to take such an undirected, edge-weighted graph and then find the least frustrating partitioning. Good. Now, when we talk about partitioning, we need to argue on a representation first. And in fact, there are two fundamentally different representations. I could have one representation in terms of the labeling of nodes. So for example, if we really do want to cut here, to make things simple for the time being, we could call, often when you have kindergarten groups, then let's say on the left we have the elephants, and on the right we have the giraffes, whatever. This would be a label for each of the nodes. Yeah? So each of the left nodes would be labeled elephant, each of the right nodes would be labeled giraffes, and then everybody knows what cluster they belong to. So by labeling nodes, we assign a label CI to each node I in our graph. And now when we talk about labels, we need to make a decision of what labels do we want to use. So a typical choice would be to say, okay, we just use natural numbers, 1, 2, and so on, up to some capital K for these labels. But in fact, they could even be real numbers, or they could be vectors. Okay, so let me write e.g. here. Or, it could be in a p-dimensional space. All right, this is the one choice. How to represent a clustering is by labeling nodes. And there is an alternative choice by labeling edges. In which case we assign a label. I'm going to call this Z, E, to each edge E in our graph. And these labels here, so these represent whether the edge is cut or not cut. I'm going to call these 0, 1 here, where 1 means cut, and 0 means don't cut. Yeah? So in this tiny example up here, the edge labels would be 0, 0, 1, 0. And if all edges are thus labeled in a consistent fashion, then I also can infer the clustering. Good. Then I've been talking about these interactions. So we need to somehow model them here. I'm going to say that we have attractive interactions. Between nodes I and j, I would call this wij plus. And I want this to be a non-negative number. And this is going to represent the tendency of my nodes I and j to be in the same cluster. And then on the other hand, we have repulsive interactions. I'm going to call them wij minus. These are also non-negative numbers, and this is the tendency of nodes I and j to be in different clusters. So back to our example, where do we get them from? Obviously from machine learning. So here's again a sketch. Top left is raw data. Then here are our neural network predictions. Then we get out the superpixels. So if you look at the colors here, you see that some of these superpixels, you can just by the shape of them, you can tell that this is not the real thing. Yeah. So for sure, these three here, I think we will want to merge with them to get a shape which is more biologically plausible. Yeah? So given these superpixels, we have a classifier that looks at each pair of adjacent superpixels. So again, these are the nodes here in our graph. And then I'm going to draw the edges. So whenever two superpixels are adjacent, we have an edge here. And then we have a classifier telling us for each of the edges whether it thinks the edge should really be there in the final result, or if the boundary should really be there in the final result or not. Yeah? So for example, just looking at the shape of these things, I'm going to guess that this here should be an attractive interaction because the boundary somehow is too straight, and also we can look a little bit at the raw image underneath and see that there's no real boundary evidence, so this is probably an attractive edge. And then let's say that this one here is going to be a repulsive edge, and we have a regression method that gives us an estimate of each of these attractive or repulsive interaction strengths. And then in the end, well, comes this magical clustering step. Yeah? So our effort to find the least frustrated arrangement, and that is then the result, which is hopefully correct. Okay, and on the bottom left here, you see again sketched this graph that we're working on. Each superpixel is a node, and then we have these interactions, attractive or repulsive, within a plane, but also between planes in such a volumetric image. And by the way, this approach here works really well. So there are a couple of benchmarks, and what I'm showing you here has the highest accuracy on some of these benchmarks and has been developed by PhD students here from Heidelberg. Good. Now, let's measure this frustration, the frustration of a particular solution. For that, we need something, I'm writing delta here, that tells me if the cluster to which node I is assigned and the cluster to which node J is assigned, if if they are the same or not. So let's say this is 1. If Ci equals Cj, and it is 0 else. And now we're going to measure frustration. So let's say the frustration, which depends on the labels. So C here is a vector. It has one entry for each node in our graph. So this frustration of a particular node labeling we are going to look on the one hand at how many nodes want to be together and are in fact in the same cluster. So we're looking at the attractive interaction here between nodes I and j. And then we ask if I and j are indeed in the same cluster. So this is good. This reduces our frustration. Hence, hence I've put a negative sign there. Okay, so this is ij want to be together and are together. This is good. So this reduces the frustration. Then on the other hand, we may have pairs that have an attractive interaction, but they are in different clusters. So here, ij want to be together if this wij is non-zero, but are in different clusters. This is bad, and this increases the frustration.
Shouldn't there be a minus over the W?
No, I'm still looking at attractive interactions.
Okay.
Yeah? So they want to be together, but they are not, and now comes the minus. You're completely correct. So let's look at the repulsive interactions. At first, the enjoyable ones. So wij minus. And I'm looking here at I and j, which indeed are in different clusters. So here, they want to be separate, and they are separate. Again, this is good. Again, this reduces frustration. Finally, the last case, wij minus. Poor guys don't like each other, but they happen to be in the same cluster. Okay, this again increases frustration. Good. This is all fine. So our task now is to minimize this frustration. However, I want to still rewrite this into a form that on the one hand is a bit simpler and which in the end will allow us to express this in the world of edges, not in the world of node labelings. Yes?
Why do we need in each line the second part? Because if we want to minimize it, if there's any attractive connection that isn't put into the first part in the first line, then we are anyway having a higher result because we don't subtract it. So we're basically counting each node that isn't connected correctly twice. Why is that a good idea?
So you're completely right. We don't need this many terms. We're going to simplify. Yeah? Why did I write it like this? Because in principle, we can have between two nodes I and j, we can have attractive and repulsive interactions at the same time, and sometimes it's convenient to estimate them separately, or to also have a measure, or to be aware if the classifier on the one hand believes strongly they should be together, and on the other hand believes strongly they should be distinct, then perhaps this is a part of the data that you want to look at manually. Okay, so this is why I kept the attractive and the repulsive interactions here explicitly. But you're completely right. We don't need this number of terms. I'm going to simplify now, and then we see if you're happy. Okay. Good. So I'm now going to rewrite this, and I want to end up with cut indicators. So I want to rewrite this whole expression such that I only have a 1 minus delta written there. Okay. So starting with the first term. I'm going to have plus wij plus, and then 1 minus delta of ci and cj. If you compare this to the first term, we now have introduced something which we need to get rid of again. Yeah? So I'm going to subtract the part that I've just introduced. So I'm going to cancel this by subtracting this. The second term I can leave as is. It already has this form of something multiplied with 1 minus delta. I'm just copying it down here for completeness. Then the next term I again copy. Because it already has the form that I want. All right, and here we do the same trick once again. We are having minus one minus delta ci cj. With the minus in front, I get the correct sign for my delta term, but I need to cancel the term that I've introduced too much, which was this one here. Good, so it's the exact same thing, just rewritten. I now have everywhere this 1 minus delta. All right, and now we can simplify. So we have twice wij plus one minus delta ci cj. And you see that we have the same kind of term with the W minus, so I'm going to subtract it here, like this. And then I have these two extra terms. Good. All right, this is still my frustration as a function of my node labeling. But if my aim is to now optimize over the labeling, I have here a term which is independent of C, independent of my labeling. So I'm going to ignore it. And I'm also not very interested in this factor of 2 in front. So I'm going to create a new function, which I'm calling E of C, where E is, let me use a different E, where E here is for energy. And it looks like this. All right, you see that here what we have is the attractive minus the repulsive attraction strength. I'm going to call this here a net interaction. Attractive minus repulsive, interaction. I'm going to call this a net interaction, and I'm just going to call it Wij without a plus or a minus. So this Wij can now be in all of R. It can be a positive number or it can be a negative number. So it's positive if attraction dominates. It is negative if my repulsion dominates. All right, and up here, if Ci and Cj are the same, then the entire thing is 0. So it's 0 for Ci equals Cj, and it is 1 for Ci different from Cj. And so I can say that this is a edge cut indicator. And I'm also going to give this a new name. I'm going to call this Zij. All right. So now we have found a representation, one in terms of node labelings. We have found a measure of frustration. We have rearranged it into an energy. And so we can now formulate the clustering problem as an energy optimization problem. So to find the optimal clustering, what we need to do is we're going to argmin over the node labels this energy function that we've just defined. This is nice because we have not really invented a particular algorithm right now. We have only posed this as an optimization problem, and then we can discuss separately, okay, now what is an efficient way to solve this optimization problem. Unfortunately, that is a hard discussion because the problem turns out to be NP hard, which does not mean unsolvable. It just means very expensive to solve as your problem gets larger or gets less well posed. So essentially, the more frustrations you have in your interactions, the harder this will be to solve in the real world. So I'm going to say this is argmin sum over I, sum over j. And then using these, I'm going to sum over those j that are connected to I. Okay, so this is a summation over all pairs I and j, which are connected by an edge. Capital E here is the set of all edges in the graph. I hope my handwriting is not so bad. So I'm summing over I, and then I'm summing over all j such that I, j are in the edge set. All right, and for these pairs I, j, I'm going to call this, edge E here, so that I can write WE here times ZE. You remember, this was the net interaction, and this was my edge cut indicator. And this edge cut indicator was defined in terms of node labels. So it was 1 if the node labels were different, and it was 0 if they're the same. And this minimization here is still over the node labels C. But now we have a formulation which is almost in terms of edge labels. In fact, I could also have written here, instead of this double summation, I could have written a single summation over the edges. So I could have, I'm changing this notation yet. You can leave your version, this is fine, yeah? But I could also have written it like this. Sum over all edges, net interaction times edge cut indicator. And the edge cut indicator is then given in terms of the node labels. But this seems like a detour. Yeah. So you see, I'm optimizing here. I'm optimizing over node labels, but my argument, what I have in the objective function, really depends on the edge cut indicators. So wouldn't it be much nicer to directly optimize over the edge cut indicators? So why not go directly argmin over Z, sum over edges, net interaction times edge cut indicator. Okay, any ideas of what's the problem here? So if I have these 3 nodes here with 2 attractive interactions and 1 repulsive, well, if I'm just making each of the decisions, edge by edge, then I would say here, don't cut because it's attractive, don't cut because it's attractive, cut because it is repulsive. But that is not a consistent partitioning of the graph. So if I only cut this edge and not the other 2, it's not clear what this means. So we need extra conditions to make sure that we get out a consistent solution from our optimization. So as I've written it here, what this means is, we would just here we would visit edge by edge, listen to our classifier, asking, does this edge have a stronger attractive or a stronger repulsive interaction? And then we would blindly follow that. But however, as I've tried to show you in this triangular example here, that's not a legit solution. So I cannot find, if I want to argue in terms of node labelings, what this tells me is that the node labeling here, if I don't cut the edge, then this node label should be the same. If I don't cut this edge, those node labels should be the same. But here, if I do cut, these node labels should be different. So it's a plain contradiction. And we need to rule out those plain contradictions, which we'll do after the break.